Welcome to the lecture series on deep learning in artificial neural networks. This video covers gradient descent with momentum. Let's start by reviewing standard gradient descent. What I plot here are two arbitrarily chosen weights. Let them call them WA and WB. Of course, there are many weights in different layers with different indices going from neuron J to neuron I. And this is now our momentary configuration at time step number 1. And the gradient corresponds to moving down in direction of the gradient, which means with standard matrix in direction of in a direction perpendicular to the contour lines. So let's say this is our first step at time step 1. The length of the step corresponds to this time step. And then at this new location, we look again at the gradient and we move down and we move down. And you see that this now develops oscillations on its way to the minimum. Now a momentum term keeps a little bit of the previous direction. In the first time step, we do the same gradient calculation and gradient update as before. However, in the next time step, we keep the gradient of the previous time step with a relative weight alpha and add to this the gradient at the momentary location. So let's see how this works. So here is our initial configuration. In the first time step, we just move down in the direction of the gradient, which in standard metrics is perpendicular to the niveau lines. Now at this new location, we evaluate again the gradient. And so the gradient would go in this direction. That was what we did before. But now we add a little bit of the old direction and a little bit, say alpha equal 0.9. So we add the direction of this previous update. And this now gives our final position here. And so the update in the next time step is this direction here. Now in the third time step, I'm now here, and now I do my update step perpendicular to the niveau lines, so roughly like this. However, I add a little bit of the previous direction, so I add a little bit of this, so that now the new update step, delta W at time step 3, points in this direction. And so you see that this gradient descent with momentum suppresses the oscillations. The first step is the same as before. The second step is this. The third step is this. So we go much more rapidly towards the minimum compared to the situation without momentum. The minimum is located here. I've picked out here an arbitrary weight called WA. It's one of these many weights that I have in my network. And this would be the position WA star, the optimum. Now, this plot here is the plot with contour lines. I can do 2 dimensions at once. Let's now plot just 1 dimension as a function of WA, of this variable WA. Well, the minimum is here, not necessarily at 0. And then while I move, if I do a projection down here, then what I would see is that it's basically some function downward with a very weak slope. On the other side, it's a function upward with a very weak slope. And here it's of course smooth. I would have this second order parabolic curvature around the minimum at WA star. I can do the same thing in the other direction. if I plot here again the error, but now as a function of WB, there's a minimum at WB star. And the difference now is that this is very, very steep. And again, there's a little bit of curvature down here. So I have one direction where things are very flat. That's this direction here. I have a valley that's flat, and I have a valley that's super steep in the other direction. Let's now analyze those two situations separately. So this is the situation in direction WA. We have this very weak slope that's more or less constant. So let's assume it's constant. This is our initial configuration, and I have a slope, I have a gradient dE dWA C, and I assume that it's the same slope over a very long distance. Of course, here at the minimum it bends over, and then there would be the same constant slope, but now rising with a different sign on the other side. Now let's evaluate these formulas. Let's look at the first time step, delta WA at time step 1. I don't have a previous time step yet, so this term doesn't contribute. So what I get is I get a minus gamma times the gradient, but the gradient is a constant, so I get minus gamma dE dWA minus gamma times C. That was the first time step. I'm now here. Now let's look at the second time step, and always just the component WA, only one of the many components. I have to evaluate the gradient, so this gives minus gamma, the slope is the same, minus gamma times C, and then I have a little bit of the previous value plus alpha times delta WA at time step 1, but that was this value up here. So in the end what I have is minus gamma times C times 1 plus alpha. Now let's do this for the next time step, and then we will recognize a pattern. So I have now minus gamma C, that's the standard gradient term arising from the first term. And then I have plus alpha delta WA at time step 2. But at time step 2, I've had this result. I have to add this gamma C. So the new result is minus gamma C times 1 plus alpha squared. So you see that if you take 10 steps in this component WA, then what we have is minus gamma C 1 plus alpha to the power of n minus 1. Here I had a 2 for time step 3. And this we can sum out. You remember what this gives? It gives a minus gamma 1 minus alpha times C. Now what is C? Well, C is just a gradient. So I have an update, and this is for n to infinity. So we have an update that is proportional to the gradient, and it's not gamma times C, minus gamma times C, but it's gamma divided by 1 minus alpha. So, so I can say I have an effective learning rate, which is gamma times 1 minus alpha. So going back to this picture here, this is my error. And the first time step was this. The second time step will be bigger. The third time step will be even bigger. So we really pick up momentum. We take up speed, and the steps get bigger and bigger. And in the limit, that have a very long slope that's constant going down. It's like working with an effective learning rate, which is gamma divided by 1 minus alpha. Now suppose we take alpha equal 0.9, then 1 minus alpha gives 0.1, then this gives something like an effective gamma that's 10 times bigger than the original one. So we can choose a very small initial gamma, and after a couple of steps, the error will be 10 times bigger if we work with this value of alpha equal 0.9. Now something very similar happens in a steep valley. Suppose that I have, when I move down here, I have a DEDWB equals C, and I make a big step. If I make a big step, I may end up on the other side. But here I have a DEDWB, which is again a steep slope, but with a different sign. And now you see that we would jump back and forth, and as long as we jump back and forth, we actually decrease the learning rate. So in that case, it does not increase the error size, but the error size gets smaller and smaller. So here again, you see how it works. We start with momentum in position W1, we walk down, we get to the new position at time step 2. These are the relative steps, and this is the final move, and from there we move on. So you see how this suppresses oscillations. There is this boring direction in which there's a speed up, and then there is a steep direction in which the actual step sizes are reduced, and so we move quickly towards the minimum, and we can do this with fairly high values for alpha. You can either take 0.9 or even 0.99. It just means that you have to start with a small initial gamma, and then the alpha close to 1 will increase the step size in boring directions. There's a variant of the momentum method which is called Nesterov momentum, and it works like this. The first step is as usual, and now we say, okay, we know that we'll use a momentum term. So with a momentum term, we would arrive here, and this is where we are going to evaluate the gradient. And then the final step is like this. So Nesterov momentum basically changes the location of where you evaluate the update, where you evaluate the gradient. Let's summarize with a little quiz. First statement, momentum speeds up gradient descent in boring directions. And yes, this is true. Momentum suppresses oscillations. And yes, this is true. And now you have two choices. With a momentum parameter of alpha 0.9, the maximum speed up is a factor 1.9, or with alpha 0.9, the maximum speed up is a factor 10. Please make your decision. One of the two is correct. Which one? And this one is correct. Final point, the Nesterov momentum needs twice as many gradient evaluations as standard momentum. Is this correct? And no, this is not correct. It only needs one evaluation per update step, just as in standard momentum.